for that. Okay, so one of the first things I want to do is go through the syllabus, and that is because it's a little bit altered from a normal semester, and there's some things that are somewhat complicated, not the least of which the fact that we're sort of going at double time compared to a normal semester, but our rooms are a little bit weird. So let's just go through that. I have some paper copies that I can pass out here. And let me just, assuming we have a sanitizer out here. That's not a classroom. But I emailed the syllabus before class. So those of you who are Zooming in can bring it up, and then I will just sort of go through it on the slides. But bear with me, everything's going to take a little bit longer trying to do two things at once. And I warned you, the syllabus looked really wordy. So that's partly because I tried to fit it on as little paper as possible, but all of the information is about twice as long as it would normally be. Okay, so let me switch back to my PowerPoint slides, if that works. Back on there. So we'll get back to that in a minute, but the first item is about the class meeting times. Now, there are times that are listed in the course schedule, and I think that's Tuesday, Thursday, 1 to 4, Monday, Wednesday, Friday, 12:50 to 3 p.m., which, wow, that's a lot of time to be meeting every day. We're just going to have to get used to that. I'm going to have to get used to it and try to pace things accordingly. But we were encouraged by the administration to be a little bit creative with that time, and also to alter the times at which we start the class on a regular basis. So today I started at the time that's printed in the schedule so that we could, there wasn't any confusion. But I would like to start meeting 5 minutes later. By virtue of taking this class, you're supposed to have all afternoons kind of only dedicated to this class. So we can take that time and sort of reuse it during then as we like. And I think what I'm going to try to do is take 1 lab's worth of period and 3 Monday, Wednesday, Friday lectures worth of period, and just even that out over 4 days. And then we will actually meet for 1 3-hour lab day every week. That's the plan right now. So it says on here on Monday, Wednesday, Friday, we're going to meet from 12:55 to 3:20. So if I take that time that's contained in one of the labs plus the Monday, Wednesday, Friday schedule time, and we cram it, redistribute it equally between 4 days, that works out to about 12:55 to 3:20. So that's starting 5 minutes later than the published time. And that is just an attempt to get it to be less crowded in the hallways. If everybody starts at 12:50, the nominal time for this, that means everybody's coming in at once, and they don't want everyone doing that. So we'll try 12:55. If there remains some sort of issue with people being late from lunch, I'm not sure if that's just a first week kind of thing, or if that's going to be a continuing problem. It seems like it's associated with not enough people being cleared, and so they really need to spread people out. So if that continues to be a problem, we can even push it back a little bit further. We've really got till 4. Everyone has their schedule open. So Monday, Wednesday, Friday, the room we're in now is Young 101, and we'll meet here. Thursdays, same times, but, oh, that's a typo on there, though. I was a little bit too quick in typing this up. I was expecting to have some sort of pointer. Hopefully you guys can see, oh, there we go. That's what I was expecting. This 0 should be a 5 there. It's 12:55. Otherwise, that would be 5 minutes too much of time. So same time as Monday, Wednesday, Friday, but we're going to meet in Young 110. That's the experimental classroom down the hall. But apparently they've reconfigured it so that there's lots of tables or desks in there and everything's spread out. It used to be small tables where people would sit in clusters. So that's Thursdays. Now, we may adjust that. It may come that I'm reserving Tuesdays for lab, and it may be that some weeks Thursday just makes more sense as a lab day, so we might flip-flop those. So I'll let you know as the days come up what we're going to be doing. I plan to stick to the Monday, Wednesday, Friday in Young 101 at these times, but Tuesdays and Thursdays we may flip. Tuesdays, the lab is supposed to be, it is in Young 131. Now, unfortunately, we have 16 in the class, and if everybody is planning on coming to lab that day, the lab can only fit 15 maximum, and I believe that includes me. So if we find that several people are planning to Zoom in, we can all meet at once. But what I'm planning to do is just kind of shorten the labs a little bit. If we're all planning on coming, having half of you come in the first half of the time and half of you come in the second half of the time, and we'll just make the labs short enough to finish in an hour and a half. We may occasionally meet in there on Thursdays too. It just depends on where we are in the material. We're going at such a different pace to me that it's hard to tell where we're going to be. So we will be meeting this Tuesday in lab, and I'll sort of survey you on Monday to see who's going to be there, who intends to be in person on Tuesday. Hopefully it ends up being pretty much everyone by then, and that'll be good. But we'll see as time goes on. The Zoom meeting ID is going to be the same, I hope, for everything this semester. So even if at the last minute you find out that you're not allowed to come, you should be able to dial into the same Zoom meeting ID you're coming to today and visit us in whatever classroom we're in, whether it's the lab or Young 110, whatever. Okay? So again, I apologize for that wordy paragraph up at the top, but that says in some detail what I summarized down below. Any questions on the meeting times? It sounds like a lot, and wow, I really hope that many of you are here every day, because I think it's going to be a lot easier to digest the material when you're not coming in on Zoom. But everything's going to be available on Zoom, and I hope, have it set up for automatic recording, and I can't really see it right now because I'm in screen share mode, but I'm hoping I'm recording this, and my goal is to sort of archive them and save them in a place where you can watch the videos later. Not that they're going to be especially scintillating, but if you can't come, for example, someday, you might want to reference those videos. Any questions on the meeting times? Okay, next big dense paragraph talks about our typical daily schedule. And I just sort of made up some daily schedule stuff here. I got to remember, I should point with the mouse so those of you zooming in can see. I imagined on September 9th and September 10th were some typical midweek days, and there's a reading assignment that corresponds that I want you to do on September 9th. This isn't a real reading assignment. The real ones will be on the website. I'll show you that in a minute. It says read sections 2.5 through 2.8 in the textbook. We'll show that in just a second. And you're supposed to post reading responses, and I'll show you where to post those. But normally what that means is by midnight on the night in which this is assigned, you should post your responses to the reading. And that's just more or less an incentive to get you to read it and sort of digest it, think of some questions or comments based on the material. There will also be, and I think I've mentioned in the emails before that I have designed the class to be a kind of flipped class, which I've never done before. I'm a little bit nervous about it because it crucially relies on the fact that you are doing certain things outside of the class so that we can do other things during class. But I thought I'm going to make all these videos ahead of time and have it be so that if we have to go all online because everything blows up at Center College, then it would be easy to transition. I already have those high quality videos made. So the videos are there. My intention is probably to do some higher level summarizing of what was said in the videos in class so that we can kind of summarize it, do discussion, and do problem solving. So you can ask your question and answer kind of stuff during class, but we're going to do a whole lot more problem solving than we would normally do in class, because you're watching the basic presentation of the logic of the derivation of things outside of class. Okay, so I'm hoping that actually ends up being a distinct advantage. So here, on September 9th, typically you'd read some sections, you'd watch some videos on that date. And on that same date, we would meet on some sections that you had already read and watch videos on. And then the next day, you're going to read some other sections, watch some other videos, and come to a class meeting to discuss the stuff that you had done the day before. Now, one of my colleagues said, you know, I'm afraid the students are just going to revolt when they see the rate at which we intend to cover things. Now, I have really pulled back the amount that I intend to cover in the course by about a quarter compared to normal. But I still think the amount we're going to be meeting in class and doing every day will be shocking. So sort of you got to adjust yourself to think, well, I'm only taking 1 or 2 classes, and I've really got to hit a lot of stuff outside of class. But a lot of the problem solving, we can't answer questions about homework kinds of stuff. That's a great thing to do in class. And I'm happy to do work at the board and discuss what went wrong on particular homework problems. We'll have a lot of time to do that, whereas normally we might have much more of a time crunch because I'm trying to present the basic locus of ideas. Okay, where are we going to do this posting, and where is this daily schedule going to be put? Well, it's on a Google site. I don't have a Moodle site for this course, so don't go look on Moodle. They create Moodle sites for every course. Mine will be completely empty. So this is in the syllabus. I think I also sent it linked. How do I open this? Maybe I can't do it from here. Or maybe I did open it, but I can't see it. If I just click, okay, there we go. So when you first go to this Google site link, you should get the typical Center College sign in. So let me sign in. And once you've signed in, oh, sorry. I see I'm not sharing the correct screen, even though I thought it was going to do so. So let me just stop sharing that and share something else. Unfortunately, I think it's put me in Microsoft Edge. So let's share screen. Here it is. Maybe I have to get out of slideshow mode. Okay. Sorry about this. I gotta get used to how all these things fit together. Okay, so now we're back, I think, screen sharing. It looks like, okay, so let me share this. Oops. Share screen here. All right. So when you log in, of course, probably for most of you, you've never had a Google site used before. But when you log in, any Google site you've been a part of will be listed there. Of course, I have lots of Google sites that I've used over the years, and here are many of them associated with Physics 110. But the one you want to look for, of course, says Fall 2020. So here we are down here. That may be the only listing for you. So I click on that. Oops. And you're going to see, I know maybe for you zooming, and also those of you in the class, it may look a little bit small, but there are 3 columns the way this is organized. The center column tells the day-by-day and week-by-week schedule. I've got to remember to point over here. Now here I've got, let me just widen this a little bit. Is that working? Yeah. I've got some empty weeks up here. We are now in week 1, which contains only 3 days, and those 3 dates are listed here. So here's today, 8/26. Boy, I know, there's a lot of stuff stacked up here, a lot of videos. Each one of those videos is probably 12 to 15 minutes long. I tried not to make them too long, okay? And it's basically a PowerPoint presentation with me talking over the top of it and pointing to things and going through derivations step by step, so it's not going to be a lot of stuff at once. I will go through the algebra step by step of things that we're doing. There's also some reading, okay? Now, the reading for chapter 1, we'll talk about some of that stuff in chapter 1 today. There's a grab bag of topics. It's not really associated so much with physics, but rather with, you know, changing units and dimensions of things, what kind of quantity something is, assumptions we can make about equations. So we're going to do that stuff today. There's not a whole lot of reading to do with it. There are a lot of other topics that we're not going to do in there. So I'm asking you to read sections 1.5 to 1.6, which mainly focus on changing units. We'll talk about that today. The first substantial physics reading is 2.1 to 2.4. And these are not long sections. You know, it's only 6 or so pages for those. That's not to say it's not dense reading. So associated with each one of those reading assignments, you accept the chapter 1 because it's so short. Like when you read chapter 1, 2.1 to 2.4, it says post responses via link at the left. We're going to go over here to 2.1 and 2.4 in the left column and click on it. And when I go there, it's empty, but I could post a comment. So if I've read my sections and there's some information given up here, the idea is you're supposed to ask questions that you have about the reading or interesting, you know, sidelines that you wish the author would have talked about. You can also respond to other people's questions that they've probed. So that means that if someone asks a question, you can reply to that. And I'm asking you to make 3 contributions. And the contribution should be well bigger than just, you know, I didn't understand what 2.1 was about. That would not count as anything. But rather, you know, when the author is saying, describing friction this way, it seems contradictory based on something else we said. How can you make these 2 things fit together? And I'll try to give you some feedback on how that's going after about a week to make sure that we're all going down the right path there, okay? 3 contributions is kind of the minimal contribution, and longer ones sort of count for more. So try your best during the first few sections, and I'll probably provide some feedback. You can do that just by typing your comment down here. And if I did that, we would see that there would be a comment down there with a timestamp and so on. Okay, so that's the left column. Let me go back to the web page here. So we've got those things, the links to the videos. The videos are on YouTube. So you just click there, it should open up YouTube and you can watch that video. The other thing that's posted there are some worksheets. So those worksheets are PDFs, and you should get something that allows you to open up a PDF. You can print it out if you want. At least for today, I brought some printed out, but for those of you who are joining us there, I think they're in the collection that I emailed before class. So if you want to open those up in PDF to follow along, I think I'll have them in the PowerPoint today, so you can just look at the questions again. Oftentimes the videos will stop and say, here's a problem to practice with it. I kind of set it up, and then I ask you to do the problem, and then when I come back in the next video, I'll go through the solution, okay? So that adds in some interactive elements in there. There's another kind of interactive element that I'll talk about that's in the videos as well. I'll talk about it a little bit. The right-hand side just shows other posted solutions to things. So I don't have any solutions up there yet, but you see I'm pointing to the syllabus for the course. So if you ever lose your paper copy of the syllabus or want to refer back, it's right there. You just open up a PDF. I'm also trying to keep the course very organized because I noticed in spring it was easy for people to get lost if all your professors were sending emails and correcting themselves and updating assignments via email. So I'm trying to keep a chronological list of emails. As soon as I write you an email, I just throw it into that link. So if you follow that link, you'll see the 2 big emails. I didn't do the ones just from today, but the big ones that I've written out that have a lot of information in them are in there. So if you follow that, here's the one that I think I sent out yesterday that had lots of things to keep in mind. Okay, that's the course webpage. And you really want to check that daily during this term because we're going at such a great rate. You always want to make sure that you've seen the latest, most update version of what you're supposed to be doing today and be ready for what we're going to do in class that day. All right. Sorry, a lot of me talking. Any questions, either from the Zoom folks or from those of you in class here?
Yeah.
For the worksheets, you said we can print them off. Is there another option?
Well, the other option is just to take out a sheet of paper and, you can either look at the problem statement and just write out your solution there. I'm not going to be collecting them for credit. They are practice that we're doing in the middle of the lecture. So if you're just reading the problem statement and you write out your solution and then you go watch the next video and you see if your solution makes sense, that's all there was to it. I will also post solutions to all the worksheets, both in the videos and ones that we do in class, over here on this right-hand side. So there's going to be a lot of solutions. Our exams, we'll talk about those in a bit. Solutions will appear up there. But all the stuff we do in class that involves problem solving that may be valuable when you're preparing for an exam, it's going to appear up there in PDF form, just scans of my handwritten solutions. But yeah, you don't really need to print them out if you don't want to. When we're in class, I will bring copies, and if certain people don't want to touch paper copies, that's fine. You're welcome to just go off of what's projected on the screen or bring a laptop and just look at your laptop, and I'll try to provide those by the time we're doing it in class. So hopefully by the end, I'm not wasting too much paper for things that people don't want in class. Other questions?
Hi, I might have missed it, but I just wanted to clarify.
Let me turn up the sound here because I was having trouble hearing. Okay, speak again, whoever was talking.
Hi, I just wanted to clarify because I might have missed it. Was that 3 contributions per response post or per week?
I'm still having trouble hearing you, or you're cutting out one or the other. And it looks like my audio is up all the way. Let me just give you one more chance. Whoever was just speaking on Zoom, can you repeat the question again?
I'll ask it for her if you can hear me better.
I can hear you now, yes.
Okay, she was wondering if the response was per week or per each of them.
Type it out in the chat, maybe.
Okay. Yeah, we're going to have to get the volume adjusted in here because however it's happening, you're sort of cutting out. If you want to type it in the chat, we can look at the question in chat. I'm hoping we don't normally have to do that because when I'm in the middle of explaining stuff, it's sort of a pain to go back and look at chat stuff. Or you can try to say it one more time.
I was just curious if that was 3 contributions per response or if it was per week. I'm not sure if I missed
Stuff.
when you said that.
Oh, there we go, yeah. So the question I'm seeing in the chat is it 3 responses per reading section or per week? And the answer is it is per reading section, and generally there will be 1 per evening. And so that means 3 questions. If it feels overwhelming, because we're not used to going into the page, please tell me, don't just silently suffer. I want it to be, it's meant to be something, not only to start a conversation, because I can address some of these in class, questions that I think are specifically very interesting. I might pull them up and discuss them as a class, and you're welcome to bring up ones that I don't bring up in class as well. But it's also a motivation for you to actually do the reading, because if you're asking a few questions, you might pay attention and say, well, what am I really interested in here? So yes, it is 3 per group of sections. So if I say read 2.1 to 2.4, 3 responses on that link that you would see on the left of the website. Other questions? Okay, this is going much slower than I normally am used to, but let me try to share this again. So if I go, let's see how this works. If I go to Zoom, share, PowerPoint, and then I go to slideshow, is that going to work? Yes. Okay. So we did the schedule, we did the daily schedule, we looked at the website. So my office is in Lamont Hall. I'm normally a resident of Olin Hall, and hopefully I'll be back in there when the construction finishes, but I'm in the basement of Lamont. It's like many of those offices, it's not really big enough to have more than one visitor in at once with social distancing. It's plenty big in a normal term. So my plan is to hold office hours every day after class in whatever room that we're in, because we should have a little bit more time in that room. So if you want to come to office hours, you can either stay right after class, or if you're on Zoom, just stay on the Zoom call. If for some reason you've gotten off, just come back on and join office hours. Usually, I don't want to hang out for an entire hour if no one's here. So if you want to come to office hours, you should come right at the beginning. That means either right after class in the first 5 minutes, or make sure you connect with Zoom in the first 5 minutes, because if nobody's here and I'm just sitting around waiting, I'm going to go and office hours will be over. So just make sure you come at the beginning. I'm happy to stay for as much time as it takes when people are here, but I just don't want to sit in this room that's not my office where it's hard to work. Okay, my regular office and phone number are in the details up there, the small print. The textbook is, well, I'm not going to bother to switch, but it's Giancoli Physics 6th edition. It's got a big, I guess this is Mount Everest, is that right? Looks like Mount Everest on the front. Big picture of a mountain. I think all the editions do. There is a 7th edition out. I chose this one because, you know, after the 3rd edition, every edition is pretty much the same. The 6th and the 7th are almost identical. They just changed editions to make more money. And so the people... Say again? Maybe someone was just unmuted. You're welcome to have the 7th edition. This one I think you can get for $30 or $40. The 7th edition is probably close to $200. I just chose it because why not? The sections, I think the section numbers are all identical, but you should check to make sure. I'm assigning reading out of the 6th edition. If you have the 7th edition, just double check with someone else that your sections line up so you know you're reading the correct sections for that day. You'll never be required to use your book in class, so even if you have, you know, an online version of that textbook, that's fine with me too. We're not going to be working through the textbook in class. A calculator, some graphing calculator is really required for the course. You know, many students have a TI calculator. I've got a TI 83 plus here, or TI 84, 85, all good. 89, 91, those ones are all fine too. Some people have the Casio Inspire ones. Some of those ones with the higher numbers can store a lot of text information in there. And I just think it's a really bad use of your time to try to store problems in your calculator. But to mitigate that, I'm going to reset your calculator to factory memory mode, so everything will be wiped out when we start an exam. If you don't want your calculator to have that happen to it, you're welcome to borrow a calculator from a friend who doesn't mind that, or tell me ahead of time and I can get one of the math department calculators for you to loan to you. Or if it's just one person, I can loan you one of my calculators too, but you got to let me know ahead of time so I know to bring it. Okay? If you're not sure if if your calculator is good enough, just come and talk to me about it. But you do need some kind of calculator that can easily do lots of trigonometry kind of stuff. You'll see we'll be using cosines and sines and tangents and inverse tangents quite a bit. And if that's rusty for you, don't fret over it. We're going to do it right from the very beginning. So from a lot of people in Physics 110, that feels very far away. There's a little in here description of a picture. This is I guess, looks like some sort of woodcut or ink drawing that shows, in my view, or the view of most physicists, what the main point of physics is, or what the goal is. The ultimate goal of physics is to unify our description of phenomena that, at least superficially, appear very different. So on the picture here, we're imagining someone's on top of a fictionally tall mountaintop over here. No mountain is that tall compared to the radius of the Earth. And they're throwing a ball at a small velocity, a bigger velocity, and a bigger velocity. And Newton is showing us that if you throw it fast enough in the direction parallel to Earth's surface, it would actually go into orbit in his description. And when he shows this, he's illustrating how the way things fall towards Earth, as we're all familiar with here on the surface of the Earth, and the motion of the heavenly bodies, like the motion of the moon around Earth, are really the same phenomenon. And so that's what we're going to try to do, is pull together a lot of things that might appear to be superficially different.
We're not seeing
Say that again?
we're not seeing the same picture.
I can tell the audio is not going to work very well. Maybe someone had a comment.
Can't see the picture.
Is that Noah? Were you saying something?
Yes, we can't see the picture that you're talking about on Zoom.
You're cutting out again. Can you say it again or type it into the chat?
We can't see the picture.
This is a good part.
Yeah. And again, I
I don't
can't.
think they can see the screen.
I can't see my chat. Can you guys not see the screen or something? Okay. Thanks for the nod. Because, okay, thank you. Let me try sharing it a different way. I apologize for that. Sometimes when I see it up on my screen, I assume that's what you're seeing. Let me try it one more time. Okay. Okay. Samantha, can you give me a thumbs up if you can see something about the final exam? Okay, great. Sorry about that. I think for whatever reason, I wasn't sharing the slideshow mode of PowerPoint, and so you couldn't see it. Thank you for letting me know. I don't know what's wrong with the audio, but it seems like every time you start a question, all I hear is, what I'm really confused about is, and then it cuts out. So I'm not sure what's going on, but it's not just one student, it's all of you. And well, hopefully most of the class isn't zooming in as time goes on. All right, so let me make sure I got what I wanted here. So here are some, now getting into the nitty-gritty details of the course, important dates to remember. Now, these are subject to change because again, I'm not used to the schedule of the center blocks term, but I'm at least tentatively planning on having exams on September 9th, September 21st, and October 2nd. Those are interim exams. And I sort of waffled about it. I thought, well, maybe I should have 2 exams, but I didn't want too much material covered on one exam, and so I thought this was best to, even though those are all Monday, Wednesday, Friday dates, you'll have to look on the calendar to see when they actually are. They're meant to be 1-hour exams, so in one of these class meetings, we would do it for the last hour of class. That gives us a chance to ask some questions or whatever right before class, pull things together. And that way, as soon as you're done, you can leave for the day and so on. The final exam, double check this, but I looked it up in the exam schedule, and Thursday, October 8th in the afternoon, 1:30 to 4:30. But as always, double check that. It would, I don't know what room it's in. We should check what room it's in because normally that's our lab room. I'm hoping it's in this room. I think it's associated with the Monday, Wednesday, Friday schedule, and I think it's in Young 101. We won't fit in the lab room, so that doesn't work for us all at once. Okay, how is the course going to be graded or scored? So those 3 interim exams, not the final exams, are scored at 16% each. The final exam, sometimes it's kind of shocking, 25%, but I'm trying to motivate the idea that you know, if you kind of flub something up in the term, but you learn it by the end, I want to give you an opportunity to show me that you can do it by the end, even if things didn't go so well on the corresponding exam in the term. So, okay, so this is 16%, 16%, 16%, 25%. That's a lot. Pay attention to those exams. That's part of all this problem solving we're going to be doing in class is preparing you to do those problems that we're seeing on the exams. So, and that's really where the rubber meets the road. You know, the lab section on here is listed as 10%. The 10% is, you know, you're supposed to come to lab and complete some stuff, and almost everyone's going to get almost all the credit for the stuff in the lab. So the lab is a little bit of padding. And it's the same way with the homework. I find that most people, I'll talk about the online homework system that we're using, but most folks, you know, with online homework, you're getting an indication if you're not getting something correct, you come get help, and then it gets, you get the problem eventually correct. So most people get most of that homework percentage as well. And so I'll talk about the short presentation in just a second, but these exam scores are really where the rubber meets the road, where I can find out if you're digesting what we're learning how to do it for most of the term there. The lab will help support that by, you know, giving you some hands-on practice with it. You know, normally I have a policy about tardiness and unexcused absences. It's a little bit strange this term in that, well, first of all, we've already been told that people may have problems with being chronically tardy beyond their control. And I'm totally sympathetic to that. That's not going to harm your grade in any way. In a normal semester in a class with 30 or 32 students, there's typically just one student who has a problem with tardiness and things like that. And this policy is meant for that student. It's just meant to motivate you to come to class every single day. So if you're having a problem with it, I am going to talk to you about it. And if it's a legitimate problem, we'll work it out. And so don't worry about it, but just be aware that I'm taking that attendance every day. And you're going to hear from me if I'm seeing you coming in late, even just a couple of minutes every day. And there's no good reason for it. So we'll talk about it if it's a problem. And the grades, you know, I always reserve the right to sort of curve things down to be more generous than this. But the default is, and typically these are kind of reasonable for center scores and the GPAs that are given out at center college. A standard scale of 90% and above is the A range. 80 to 90% is the B range. If there's a disaster on some exam, and there may well be because of the rate that we're going through stuff this semester, I'm not just going to say, well, everybody just eat it and you know, forget about it. We'll make some adjustments and try to figure out how to deal with it, but that's the going in position here. Okay. Now, the next slide is telling us about this short presentation. It's worth almost 0, but it's just something you have to complete. And the idea is that for no matter who you are, this course is a general education course for you. General education is all of a sudden switching right now to mean some new things. Now, this course is a new general education course and an old general education course. The presentation, that short presentation, is meant to cover some things that normally probably wouldn't be covered in the same way in a physics course. So if you look at the catalog description of the general education physical science courses, we're supposed to, of course, have some understanding of some of the concepts and tools of physics and the ability to use them. Of course, we're going to do that lots in the term. But it's these last two, oral or written communication involving creative or critical thinking, and recognition of connections to wider social issues, personal choices, and values. That isn't typically, you know, you're not going to find that in Giancali's textbook, a lot of that kind of material in there. And so a way to sort of keep us making contact with that, what I'm going to do is have you each do a 5-minute presentation at the start of a class period someday during the term. Okay. I haven't quite decided yet. I may even allow you to work in pairs. Typically, I allow people to do it either by themselves or in a group, as long as we're socially distanced while you're giving the presentation out here. And I will give you more details about that probably by the beginning of next week. So don't worry about it right now. It's something you need to do once. It's more or less a check the box if you've done it. And it is to make connections with things of personal interest, things that are of career interest to you. In Physics 110, we have a lot of people who are interested in pre-health, pre-med kind of things. So a lot of times they make connections with science and health topics, body scanning, that kind of stuff. Or student athletes will make connections with their particular sport and talk about the physics of their sport or some science related thing. So we'll talk about that by early next week. Let's try to just get going with the rest of it before we worry too much about that. Again, I apologize, just a lot of small print here. I'm not going to read through this, but generally up at the top, class preparation and participation is saying you need to do those things outside of class, and part of the way of motivating you to do the reading is those online reading posts. So you should be following through and doing those on the day that they're assigned. And come prepared to participate in discussion. Hopefully this is the last day when I'm giving more or less a monologue to you. And what it's going to be is more Q&A, a lot of problem solving where we're looking and trying to diagnose what's going on so that you feel really comfortable with the kinds of problems you'll see in the homework as well. So try not to just lurk in the back of the room, but rather be someone who participates, asks questions when you have them, especially with this trying out the flipped kind of class. That gives us a lot more flexibility for doing stuff in class, and so you should get your questions answered in this time. So attendance, especially this semester, is going to be required every day. So I'll be taking attendance every day and making sure everyone's here. If you're not here, I can't remember if it's for one meeting or two meetings, I have to fill out a report that there's some emergency situation and a student has disappeared. So if you're not able to come, first of all, communicate with me and let me know that, hey, I'm sick, I don't have COVID, or I did test positive, or, through contact tracing, I'm forced to be in isolation now, or whatever they call it when you're someone who needs to get a test and wait until you're free to come back around campus. Just let me know what's going on so that I can have an idea of where you are. Normally, there's a big discussion of excused and unexcused absences. Well, the biggest cause of excused absences is athletics, so we shouldn't be seeing so much of that this term. And I'm not sure how many other excused absences. The associate dean is free to excuse you for other kinds of things, which are actually pretty rare compared to athletics. But if you have an excused absence that's coming up for whatever reason, let me know about it so that we can work around due date deadlines or whatever. Unexcused absences is everything else, like you slept through class because you stayed up studying or something like that. Everybody knows what unexcused absences are. And those can come back to bite you by that syllabus, deduction that was in the grading part. So please talk to me if you have any sort of absence, so especially this semester, to be very clear about what's going on. Tardiness, again, if it becomes a problem, I will talk to you about it. For the most part, it's not a problem for 98% of Physics 110 students. So I'll let you know if it's a problem. If you have a special medical condition or disability that requires some sort of accommodation, you should, first of all, have talked to Dr. Brian Cusado, who is our new contact point, I think, for accommodations for disabilities, and get an accommodation notice and then talk to me about it. If it's something that requires accommodation during exams, we may have to think well ahead of time before the exam how we're going to meet that accommodation. So if you're someone who has that, then let me know what accommodation you need. There's a big section on academic honesty here, and I'm not going to read through it again, but the upshot is some of this was put in the spring when we were doing online stuff and people were taking online exams at the end of spring. But you're expected to, when I say you're not allowed to talk to anyone or use other resources, even if we're not present in the room, I hope to be present in the room. But if you're not present in the room, you're expected to abide by those. And there is an extra discussion of what that means for homework. I really do want you to collaborate with each other as much as we can, staying socially distanced, but you know, students often text about stuff and whatnot. To collaborate on homework is just fine, and I encourage it. You should know after you come to a group solution for how to solve a problem, how you solved it. If you are writing down something or doing your homework online stuff, and I'll talk about that at the end of the syllabus, if you're filling in an answer that you don't know how you got, that probably is on the cheating side of things for homework. So just keep that in mind. You know, you may get that homework problem right, but the exam where it really matters, that's where you're going to suffer on it. So if you're not understanding how to do a homework problem, sure, work with your friends or other people in the class, but make sure that you get your question answered to your satisfaction so that when you're asked to do that problem again, you can actually do it. Okay. The last page has a lot of details about our online homework system. Okay, many of you I know have used things like WebAssign or Mastering Chemistry. I found a couple of years ago that those all of a sudden were getting much more expensive, you know, over $100 for the semester. So I made a decision to go to one that was less expensive and still good enough for what we're doing. That's run out of the University of Texas. It's called Quest Learning and Assessment. And it does, you do have to go through one additional hoop to sign up for it, and that is you have to be assigned an ID number for the University of Texas at Austin. And so the details about how to do that and a link to where to go, or you could just type it in if you don't have the electronic version of this syllabus. Follow this link, which is also given down here at the bottom of here. And if you follow it, it's going to take you to a page where one of the options is to sign up for a UTE-ID. That's step number one. Once you've done that and you go to Quest Learning and Assessment and click on the, you know, if you Google it and click on the first link, one of the options you'll see at the lower left corner is enroll in a new course. And if you click on that, it will ask for a unique ID number, and the number for this course is 1001. Now, it's not quite unique. There may be 3 other courses in the country that use that number, but you'll see one of them says Center College Physics 110. So, of course, the one you're going to select. And that will allow you to enroll in the course. And then in the future, when you come to that website and you log in with the username and password you're assigned, then when you click on our course name, you will go to a place where you see the assignments, the ones that have been assigned already. So right now you probably wouldn't see anything, but hopefully by tomorrow, or maybe even the end of today, I'll have the first homework assignment put up, which has to do with chapter 1 and chapter 2, because we're going to get into a little bit of that today. Okay, so this homework system is, I believe, $30 a semester. And I'm hoping that because you could save a lot on the textbook, and this is an inexpensive homework system, that it's not going to be so expensive of a semester for doing this. Any questions on all of that stuff? Again, I apologize profusely for giving a monologue on this not very interesting stuff. I like to talk about physics, but not so much syllabi. Just listening for the benefit of the Zoom folks. Okay. Oh gosh, I thought I was done with this, but there is, let me just point out, there's some information about how your answers are scored in Quest that you should read down there. For a numerical answer to be considered correct, it has to be within 1% of the correct answer that they're expecting. And so they're calculating the correct answer by a formula, and your answer has to be within 1% of that. there are occasionally multiple choice problems, and the multiple choice problems are scored differently because if there are only 5 choices and you make 4 incorrect answers, by process of elimination, you know what the correct answer is. So it goes down by a reasonable fraction. So by the time you answer 4 questions incorrectly, the last one you get 0 credit at that point. Okay, so read the details there. It also tells about how to enter things in scientific notation using that E notation. And that will be important for us later in the semester. So if you're, just remember, if you're trying to enter scientific notation, you don't do something like times 10 to the 9th, you do E9, and that means times 10 to the 9th. Try to remember that so that when we get there halfway through the semester, you'll remember to go look at the syllabus or ask about it. I know this system is completely new for almost all of you. It's much more rare that people use Quest. So I'm going to be very patient about it. If you're having problems getting into the system or seeing our assignments, or if Quest went down and you couldn't do it and you need an extension, that's all fine with me. Just communicate with me and I'll be very patient about it. And please be patient with the system and with me. We'll get it all resolved, but just make sure if you have a problem, communicate it with me quickly. Because of the pace of the semester, we really need to make sure that things get resolved sooner rather than later. Okay, so what I would suggest, I don't think I put this in today's action items, which seems ridiculously long already, but you should try to log into Quest, get your UTEID, and just see if you can see our course. And if you're, if you can't do it by Friday, we really need to start working hard to figure out what the problem is. So if you can try to do that today, follow those instructions, get your UTEID and see our Physics 110 course on there. That's really all you need to do for right now. And I don't think any assignments are up there, but I will put the chapter 1 and 2 up very shortly. Thus ends the discussion of the syllabus. Any more questions on that before we move on? Yes, Jeremy.
So are there going to be different homework questions on this, and then there's the other ones, like the things that'll be on a PowerPoint or
So the things that will appear in the PowerPoint or that I'll pass out in class are not considered homework questions. I consider them class exercises, and those I will not collect and give credit for. They're a chance to say, hey, we talked about something. Now I'm going to see if you can see how to apply it in the context of this problem. In many cases, those class exercises are a little bit easier than what you might see on the homework or the exam because they're the first example we see. So take that with a grain of salt, but I will provide solutions to all of those. Generally, I don't provide solutions to the homework, although I'm happy to on any particular problem if you want to see it work through how to do the problem. Okay. All right. A couple just more quick motivational things before we begin, and this may be relevant to when you're here in class. It's going to be hard to do when you're Zooming, but you'll also see something related to this in the videos that you'll be watching. Learning involves building new neural connections, and the research shows that in order to help build new neural connections, being actively engaged in what you're doing, not just sitting like we're doing today. This is the worst way to learn something, and I apologize again. Any way that you can get involved in thinking about how you would answer a question or working with other people as much as we can while staying distanced from each other is going to help with that. So we've got to rewire those neural pathways, and that means interactively engaging. Sometimes that means arguing, taking a stand on something. If you think what the author is saying or what I'm saying makes no sense, or there's a special case that seems to violate what we've been talking about, take that stand. Someone else may argue against you, and both of those, that process really helps in the learning. But it also means solving problems or answering a question that might seem a little bit tricky or ambiguous. So we're going to do a lot of that during the semester. It certainly does not mean listening to me explain or taking notes on how to do it. That's the kind of stuff that we don't want to do for long periods of time. Of course, a certain amount of explaining should happen, but we never want it to happen for a very long period of time. So in order to do that, normally many of you have probably experienced doing clicker questions before. I'm going to do something similar, although I tend not to use clickers. You'll find, and haven't decided if I'm going to do this in our class meetings or not, because I've worked some of these into the videos you'll be watching. And I just ask you to, while you're watching the video, here's 5 multiple choice answers. Choose in your mind the one you know is correct. Pause the video until you do it, and then unpause the video, and I will discuss the solution. And I'm happy to discuss it more in the class time if you want to. So this would just be an example. Here's a bunch of different directions, numbered 1 through 8, and the idea is here's a block sliding down a slippery ramp. It jumps up, and the question is, what is the direction of the acceleration of the block at position R? Which way is it accelerating at that time? I don't expect you to know anything about that now, but we will talk about that very shortly, at least in chapter 3 is when we'll first get to it. So don't expect to know that, but this is just the kind of thing that you might vote on in the process of watching the videos. And if I decide to add more of them in, I may do it in class, and I'll give you an easy way to vote when we're in class. I didn't emphasize, in a normal semester, I do talk a little bit about keeping a growth mindset. Many people have heard about the comparison between a fixed mindset, saying things to yourself like, I'm just not very good at math, or I'm not good at physics, or I really am good at physics. That's another kind of fixed mindset. It means I'm making a statement about myself that makes it sound like a permanent property of myself. Contrasting that with a growth mindset, which is the point of view that if I work at something long enough, I'm going to have success with it. And so here are some growth mindset quotes. Einstein, it's not that I'm so smart, it's just that I stay with problems longer. Nelson Mandela, do not judge me by my successes, judge me by how many times I fell down and got back up again. So it's all about keeping trying. Don't get discouraged by the process. If I have the idea, even if I have what might seem like a positive idea that, hey, I'm really good at physics, then I hit a problem where I just can't solve it on the first, second, or third try, I may start to doubt that. And that's one of the reasons why any fixed mindset about yourself is not a good idea. Rather the mindset, if I just keep going, it's going to work out. A genius. For 37 years, I've practiced 14 hours a day, and now they call me a genius. And it takes 20 years to make an overnight success. Sometimes during a regular semester, I might pepper those throughout the presentation. I probably won't this semester because I'm trying to cut things down because of the speed we're supposed to be going at. Please do communicate with me if you feel like you're just drowning in stuff and you're trying as hard to keep up as you can. Let me know. Don't just silently suffer, because it is kind of an experiment that everyone is doing on campus this semester. We've had center term before. Even you first years kind of know what the idea of center term is. But really, for those center term classes, people have hand-designed the classes to fit into center term, and so they're sort of made with that in mind. Whereas now we are teaching courses that have a standard amount of material that is supposed to be taught, and we're trying to cram them into this new format. It may or may not work, so let me know if I can help you, or if you feel like you're just drowning in some way. I need to know that so that we can accommodate somehow. All right. That's the end of the introductory stuff. Let's see. It's been about an hour. Let's just get up and maybe stretch. I guess we're not supposed to get near each other, but it's been an hour. Let's just take 3 minutes break, and then we're going to start talking about chapter 1 material. Okay?
Is everybody a freshman, or is there?
Not everyone in here. Is everybody a freshman except? But she's an RA for a freshman dorm. Is that everybody else a freshman? Yeah. Okay. So the upperclassmen have not gotten, unless they're an RA for a dorm, they haven't had enough time yet. And I guess even if you were an RA for an upper class dorm, you're staying with your pod of students that you're working with, so you still wouldn't be cleared by virtue of being in contact with them. Okay, so chapter 1, let's get into it. The hope is that most of these things you have encountered before. You may be rusty with them, so we're going to practice a little bit with them. We're first going to talk about what dimensions mean. That's not as commonly a used term, but units, most people know what units in which you would express stuff. So what's the relationship between them? That's first. Second, and by the way, I should say, this presentation that I'm giving right now is actually duplicated in one of the first chapter 1 videos. So what you're going to see there is me talking over the PowerPoint and doing exactly the same stuff. But I know you haven't watched it yet because it's day 1. And it may be easier to digest in person, so I'm just going to do it this way today. We'll then talk about scientific notation, what that means, and the SI prefixes. Those are things like milli or kilo, those kinds of prefixes. We will use certain limited numbers of those in this class, so you need to know what they mean. How to change units. You know, if I know something in feet per second, if I know a speed in feet per second, how do I get it in meters per day? Most of you have done some of that before in some high school science course, probably, but a lot of people are rusty with it, and so we'll do the hardest kind of problem we can do, which is not that hard, but hopefully it'll warm you back up to it. A discussion of significant digits, how many digits you write down when you're giving an answer to the problem and carrying enough when you're doing calculations. And then finally, something called dimensionally balanced equations, which probably doesn't mean anything till we get there, but it'll be important for us this semester. So dimensions and units first. The question physicists are most often concerned with, at least in saying, what kinds of things are there out there? Well, in physics terms, often that means what measurable properties are there about things. You know, a thing may have a mass, or about events. How long does this interaction between two particles take? Or what's the volume of an object? Those are measurable properties of things that, or events in the universe. And all those kinds of things are called dimensions generically. So for example, in physics, some dimensions we might be concerned with, the weight of an object, the mass of an object, and we will talk about the difference between mass and weight. If you don't know that, you know, at least they're usually somewhat confused in the way we speak commonly. The length of an object along a certain direction, the volume of a 3D object, how fast something's rotating, the rotational rate. Energy, we'll learn about energy and what that means. Temperature, right? How hot or cold something is. Those are all properties and they're different, right? Temperature is a different kind of thing than mass. We all know that, right? So we call them different dimensions. Now, this may seem a little bit overwhelming because here's just a very short list. We're going to have a lot more than that that we will encounter just in Physics 110. So there are a lot of different dimensions, but the saving grace that simplifies everything is that some of the dimensions can be expressed in terms of other dimensions. For example, if I've already sort of become comfortable with dimensions of a distance and a time, I can represent a speed as a distance divided by a time. And so even though I may have a list of 25 different kinds of dimensions we're going to be interested in Physics 110, amazingly, we can express all the dimensions we will need in Physics 110 in terms of 3 what we might call fundamental dimensions. So we can have a huge list of kinds of things we could measure, but at least for the ones we're going to deal with in Physics 110, at least in this term, we would need to add one more if it were a normal length term because temperature is a little bit different, but we're not going to get to temperature in fall 2020. The fundamental dimensions are length for us, length, time, and mass. There are other ones, you know, so like electric charge can't be expressed in terms of those, but we're not going to talk about electric charge. We used to in Physics 110, but we just don't anymore. So for example, you know, I already said if you want to specify a speed, you could do that as a length or distance divided by a time, and so on, right? Density, well, I'm assuming that most people have some sense of density, how heavy, how massive something is per unit volume. So a density would be like a mass divided by a volume, and a volume is like a length cubed kind of dimension, right? So we can express all the dimensions we need in terms of those fundamental ones. What most people are more familiar with is the units associated with dimensions. So here I want to talk about the units we might use to measure length, time, and mass, right? Length I might measure in feet, or inches, or meters, or kilometers. There are lots of different units we might measure for length. So just to give some examples, I might measure length in inches, abbreviated IN, time in days, and mass. The English unit for mass, maybe some of you have heard before, is called the slug. You can look up how a slug compares to a kilogram in the back of your book or the front of your book. They would tell you what the relationship. We're not going to use slugs, but that's just an example. Another length unit is feet. Another time unit is year. We will use years when we're talking about the motion of, you know, astronomical objects, like the time period that it takes a planet to go around the sun. We wouldn't want to use seconds as much as years, because typically it's going to be a much more manageable number when expressed in years. And mass could be expressed in grams. Now, the system of units we're going to stick with more than anything, and that you're probably most comfortable with from high school courses, is called the International System, or SI system of units, for which we're going to measure lengths in meters, time in seconds, and mass in kilograms. And sometimes people at the very beginning get confused by this, because you might think, well, a gram should be the fundamental unit for SI, but it's kilograms for whatever reason. I don't really know, but the kilo goes up in front. So kilogram is a pretty hefty amount of mass. You know, if you think of a typical full can of Coke or something like that, it might be 2 or 3 times that mass. So it's something that weighs quite a bit. I probably should have, in a normal semester, I would have brought a kilogram mass and passed it around, but that's probably something we shouldn't do this semester. Now, if someone, you know, a homework problem might give you something measured in inches, and you want to convert it to meters so that you can give your answer in SI units. So we have things that tell us the relationship between different types of units. They're called conversion factors. 1 inch is exactly the same distance as 2.54 centimeters, or, you know, I've lopped off some of the exact numbers there, but all those kinds of conversions that you'll ever need in this course are in the back of your book, or you can just Google them. You know, you would say inches to centimeters in Google, and it will tell you the conversion right away. So anytime you need those, feel free to just Google them, or look them up in the back of your book if you have it handy. Okay, so that's about dimensions and units, which are how we measure those dimensions. Second, scientific notation first, and then a little bit about SI prefixes. Why do we need scientific notation? Well, here are some distances that people might be concerned with in physics. From very, very large distance, at least at the time I grabbed this slide from the web, the distance to the farthest galaxy was estimated to be about 10 to the 26th meters. That's a 1 with 26 zeros after it, and then a meters. That's a lot of meters. Not a number I want to write down either, right? If I didn't have scientific notation, I'd have to write all 26 of those zeros as placeholders so the person would know what I'm talking about. All the way through normal human kind of size objects down to things that are even smaller than a proton, but the approximate size of a proton is about 10 to the minus 15 meters. That would be a decimal point with 14 zeros after it and a 1. Again, very terribly inconvenient and hard to read too, because I have to count the zeros and I may miss one and misunderstand. So we use scientific notation because one advantage, we'll see another advantage later. One advantage is that we're talking about very large or very small distances, they allow us to express them compactly in a way that's easy to read for human beings. So for example, if somebody asked you the distance from LA to New York City, I looked it up on the web. It's almost 4 million meters, 3,961,000 meters approximately. That's a cumbersome way to express it. And when someone tells me something in millions of meters, I really don't even have a sense of how big that is. Now here I do, because I know it's the distance from LA to New York City, but maybe in a different problem, I don't have any intuition about it. It's somewhat simpler, or at least easier to digest if I can write it in scientific notation. That's okay. That doesn't make it a whole lot better, but that's 3.961 times 10 to the 6 meters is scientific notation. But another way I might express it is in terms of kilometers. So we have these prefixes. I'm so used to pointing at the screen, but I got to remember to point with my mouse. We have these prefixes like kilo. They're called SI prefixes, and kilo, for example, means times 1,000. So a kilometer or kilometer is 1,000 meters. So here are some of the SI prefixes that you can find listed in the book, and most of these we are not going to use. We're only going to use the ones that you're probably commonly familiar with seeing, for example, in newspaper kind of stuff that I have boxed right here. Very occasionally you'll see nano expressed in the book, like for nanometer scale things or nanotechnology. Nano means 10 to the minus 9. So if we're talking about nanometers, that's 10 to the minus 9 meters, or 1/billionth of a meter. Micro, so nano has the abbreviation lowercase n. Micro has the abbreviation lowercase Greek mu. Okay, that's like a U with a little tail on the left-hand edge, but it is the Greek letter M, so it's like a lowercase m in Greek. Micro means 10 to the minus 6th, or 1/1,000,000th. So a micrometer, sometimes people abbreviate it as a micron, is 1/1,000,000th of a meter. Milli, almost everyone's familiar with, lowercase m. A millimeter is 1,000th of a meter, 10 to the minus 3 meters. Centi, 10 to the minus 2, so a centimeter is 1/100th of a meter, and kilo is 10 to the 3, or 1,000. So a kilometer or a kilometer is 1,000 meters. You don't need to know the other ones. You can look them up if you need them, but these particular ones might just be thrown into the wording of a homework problem or even an exam problem. So if you're not familiar with those, you're welcome to ask if you're ever thrown off by it. I remember many years ago, there was a student in Physics 110 whose name was Millie, M-I-L-L-I-E, and she came during an exam and said, I don't know what this little m means here. What does that mean? Well, it was sort of ironic, I guess. All right, so that's about SI prefixes and scientific notation. Here's really the point, that the biggest thing I wanted you to practice with in this chapter 1 sections that we're talking about. Again, we're not talking about everything in chapter 1. When you do the reading, you'll see I only asked you to do sections 1.5 and 1.6, which concentrates on some of the things we're talking about here. Changing units, it's not that exciting, but we want to make sure that we know how to do it. And I thought I'd just throw up a voting question without discussing it at all to see where everyone's at. And don't feel bad if you get lost in doing this, but I want you to try to do this question without any explanation. And I will explain it one way that I know how to explain it. If you do it a different way and you know how to do it correctly, that's fine. I just want to make sure that everybody knows kind of how to do it. And then we'll go on and do a problem on paper that's a little bit more difficult and is about as challenging as it's going to get. Not that much more challenging, but sometimes confusing people. So a 3D printer head can move at a maximum speed of 4 centimeters per second. How do you express this speed in units of inches per minute? And by the way, if you look up in the back of the book, 1 inch is 2.54 centimeters. So see if you can reach back to your high school chemistry days or wherever you learned how to do this kind of stuff and pull that out of your brain and see only one of these is obviously the closest correct answer. So if you keep enough places in your calculator, you'll find that only one of them makes sense. And we'll do it together after you have a chance to do it yourself. I guess for those of you who are in class, I actually do have a worksheet, and it's got another problem on it that maybe we'll get to on a different day, but I'll pass it out. Anyway. So if you get an answer that's very close to one of those, you're pretty much sure that it's correct because I didn't put any sucker answers on there. The other three are just kind of random numbers I chose. Oh, I'm sorry. The one on the worksheet isn't the one we're doing now, but we'll get to that in just a second. Again, if you're having difficulty, don't beat yourself up over it. I know I didn't tell you anything about how to do this. I just want to kind of see if you have some distant memory of how to do this if you're not used to it. And we will discuss from the very beginning how to do this in just a minute. So if this were more of a normal class, I would probably, and everyone were present, I might have everyone actually vote on it, but I'm just going to dispense with that. You know whether you got it right or not just by whether you're close to one of them. And in this case, let's just go through the solution. Normally I would do this on the board, but I think it'll be easier if I click through the step-by-step instructions on PowerPoint. It'll be easier for the Zoom folks to see. So I start out with the number that we're given here. The thing we're interested in is 4 centimeters per second. I will talk about significant digits and what to do with those 0.00 later, but it's the number 4 in centimeters per second. And I'm going to do something to this 4 that doesn't change it at all. In other words, I want to be able to write down another number in different units, which is exactly the same, which is to say it's equal to it. It's just expressed a different way. One thing you can do to any number with units that doesn't change it is multiply by 1. If you multiply by 1, you've done nothing to change that number at all. And one way to create the number 1 that seems a little bit odd is to put something that's completely the same in the numerator and denominator of a fraction. If I put things that have no difference in the numerator and denominator of the fraction, I've created the number 1 in that ratio. So here I'm going to form the number 1 out of, well, 1 inch is exactly the same as 2.54 centimeters. So that ratio, even though it looks like something complicated, is the same as the number 1. And when I multiply by it, I don't change what this number is at all. I'm just re-expressing it in an equivalent way. Why did I put the inches in the numerator and the centimeters in the denominator? Somebody help me out with that in the class here. Yeah, I'm looking for a cancellation. In other words, I don't want centimeters in the numerator. What I want is inches in the numerator up here, right? So I want to get rid of the centimeters and replace it with an inch. So I've got the inch in the numerator and the centimeters in the denominator so that there's a cancellation in the centimeter units. Okay, that's great. I'm halfway there. I replaced my centimeters with inches. And now I do the same thing to replace the seconds with minutes. I'm assuming that everybody knows that there's 60 seconds in 1 minute. So another way I can multiply by 1 is to put 60 seconds in the numerator and 1 minute in the denominator. Again, the motivation for putting the seconds in the numerator is I had a seconds in the denominator. I wanted to get rid of it. So I'm going to put the seconds in the numerator in this factor of 1 over there so that they'll cancel out. So I do that cancellation. And then I look at all the stuff that's left, combine all the numbers. So I have 4 divided by 2.54 times 60 is all the number stuff. So I put that in my calculator. And the units that go with it that are left after the cancellation are inches per minute. And when you do that, at least this is what I had written down from the results of my calculation, 94.48818. If I didn't do, we haven't talked about significant digits yet, so I just gave a whole lot of digits there in inches per minute. That's very close to the first one, so it seems like A is the most reasonable answer. Anybody have any questions about that process? And again, if you do it a slightly different way that feels a little bit different, but you're comfortable with it, that's fine with me. I'm not going to check your work on this. I just expect that you can do this kind of stuff. Okay, so for those who were in the class, I just passed out a worksheet that has this first question on it. For those of you who are zooming in, here it is. We're told that water flows from a faucet with a certain volume flow rate. Volume flow rate means in a certain amount of time how much volume comes out. So this faucet has a volume flow rate of 50 cubic centimeters per second. We want to convert this to cubic meters per day. The reason I'm asking this is because sometimes that cube messes people up. So try to calculate that number, and then we'll do it together. But, take 3 or 4 minutes to see if you can get a number there. And when most people in the class look like they're done, we'll go on to the solution. Okay, it's looking like more than half of the class that's present here is done calculating. So let's just go through the solution. I'm going to approach it the exact same way. Write out the number that I'm starting with and then try to multiply by 1 a few times to turn it into the kind of units that I want. The first factor of 1 that I'm going to multiply by is to try to get rid of the centimeters cubed in the numerator. Now, I've got centimeters cubed means centimeters times centimeters times centimeters. So I could do them one at a time. Just get rid of one factor of centimeters. I want it in the denominator because I have a centimeter times centimeter times centimeter up here. And I could at least get rid of one factor of them by using the fact that 1 meter is exactly the same thing as 100 centimeters. I was assuming that you remembered that fact about centimeters. Most of us have used centimeter rulers in the past. Okay, so there's my factor of 1. That would allow me to cancel out just one factor of centimeters up here, and I'd have 2 more factors of centimeters left. I'd have to do that 3 times. I'm lazy, so instead of doing it 3 times, I'm just going to put a little power of 3 on this. If this is 1, multiplying by 1 is fine. 1 cubed is 1, so multiplying by 1 cubed should be fine too. Why am I doing that? Well, when I cube this whole thing out, I know, oops, I know I will have a 1 meter cubed up here, right? Everything, when I cube this out, everything in the numerator gets cubed, everything in the denominator gets cubed. So it will be 1 cubed meters cubed divided by 100 cubed centimeters cubed. And then I can cancel that centimeters cubed against the centimeters cubed up there. And because I'm lazy, I'm going to do the cancellation like this. It looks like I've canceled a centimeter against a centimeter cubed, but really that centimeter was inside a cube. So when I get rid of it, when I remove it, I really remove 3 factors of centimeters from the denominator because it was cubed, and now there's nothing being cubed anymore. Okay? That replaces my centimeters cubed in the numerator with now a meter, which is being cubed in the numerator. And then the last factor of 1 is, well, let's see. I need to know the relationship between seconds per day, and I'm assuming most of you can figure that out, even though it may not be in the top of your head. In one day, there are 24 hours, and in each hour, there are 60 minutes, and in each minute, there's 60 seconds. So there's 24 times 60 seconds in a day. So that's a factor of 1 there. And now I can cancel my seconds factor from the numerator and denominator. And the only units that are left are meters cubed. You want to make sure you don't forget about that cube there per day. And that's what I wanted. So putting all the numbers together, I have 50 divided by 100 cubed. That's a place where people might forget about that cube, but I have to divide 50 by 100 cubed because that 100 is inside a cube in the denominator. Times 24 times 60 times 60. That's the number, and the units are going to be meters cubed per day. So approximately, if at least I round to 2 places after the decimal, you get, according to my work, 4.32 cubic meters per day. If you can do that kind of problem, that's as tough as it's going to get in Physics 110. So we're just trying to make sure that everybody has the tools. This isn't the physics, but it is a tool that we need to do the physics almost every day during the term. So you want to make sure that if you're having trouble with this kind of stuff, or for some reason you didn't get it in high school, come and let me know, and we can do more practice problems. I can assign you more problems. Most Physics 110 students are, it's somewhere in the back of their head, and they just need to bring it up to the front again. Questions on that? All right, there may be 1 or 2 problems in the homework that ask you to do something like that. Okay, last topic in this grab bag, which is chapter 1, is, it's the second to last topic, significant digits. That's how many decimal places you specify when you're giving an answer. And I've been pretty cavalier about it so far. But I want to give an example of why we should be concerned about this thing. Suppose I calculated my height in my calculator because I knew my weight and I knew my body mass index. And so through those, I could do a little calculation in my calculator, and this is the number I got out. my height is my calculator gives lots of decimal places. So out of my calculator came 1.827448603 meters. And the question I want to ask is, what is ridiculous about the number, or why should I be a little bit embarrassed if I write this down in a public place? Certainly if it's in a report that I'm going to report to someone else, it would be embarrassing to say this number. To what degree have I specified my height? To what, do I know it to the level of a centimeter or a mile or what?
One of those small ones you said we're never going to use.
Yeah. Well, no, we're still in the range of the ones we're using. Let's see. So this is 10th. I'm sorry, I should point with I forget that there are people zooming in. Let me point with the thing on here. This is tenths of meters, hundredths of meters, thousandths of meters. So if I specified only to that 7, that would be to the nearest millimeter. This is down here, 10 to the minus 6 meters. So if I specified to the 8 there, that would be to the nearest micrometer or micron. And down to this last 3, that would be 10 to the minus 9 meters, which is nanometers. So I specified my height to the nearest nanometer. Now, maybe I have a really good measuring technique for doing this. Why would that be ridiculous to make that statement? Even if I said, I've got the best height measuring thing in the world, it just makes no sense. Why is that?
Because we can't see a nanometer with our eyes. It's too small.
Well, we couldn't see with our eyes, but suppose I have some laser things with mirrors and, it's all very precise and official looking. And I claim that I said, now I know it. This is my almost exact height. Why would that be a ridiculous statement to say about my height?
Nobody cares that much. It's too specific.
Yeah, nobody cares. It's not only too specific, but it's just not defined that much, right? What are you mashing my hair down with a certain force? How are you doing my hair, and how straight am I standing up? If I stand up straight like that, I might move by a half a centimeter, let alone nanometers, right? So we're not going to spend too much time talking about significant figures in Physics 110, but I do want you to be reasonable in the numbers that you write down, and just try not to make a fool of yourself because a lot of students, this from previous classes, that students tend to write down everything that comes out of their calculator because I just want to be safe and not give too little. But sometimes it can be really ridiculous. So I would say, my height's not even determined to the nearest millimeter. It probably, if you had some consistent way of mashing down your hair, it could be determined to plus or minus a centimeter. So maybe this place right here makes sense, but this millimeter place probably doesn't make sense. How do I know that it's 7 and not 8 millimeters that goes in that place? So if I'm going to report this number, I would always, decide to what degree I know this value and then round to that particular place. So if I say, I kind of could know the nearest centimeter. There's no way I know the nearest millimeter. Then what I'm going to do is round to the centimeters place. And because this next digit was a 7, it was 5 or bigger, I'm going to round that centimeter place up to the next digit. So 1.83 meters in this case. So the overarching rule here is just be reasonable and try not to say something that's ridiculous. Typically in this course, we are going to use 3 significant digits when we report an answer. So that means when you're calculating something in your calculator, you probably ought to keep a lot of decimal places for the intermediate calculations. But when you're reporting your final answer, make sure that you use 3 significant figures. Now, how do I calculate the significant figures here? Well, I start with the first non-zero number on the left, that's a 1, and I calculate all of them that are specified there. So in this case, I'm counting 1, 2, 3 significant figures, or sometimes people call them significant digits, okay, or sig figs for short. And we're generally not going to think about it too much this semester. Now, the one place you probably do want to be careful about it is in doing that online homework, where your answer that's given has to be within 1% of the answer that has been calculated from an exact formula. And that means that you probably want to keep more places. And when you get to the final answer, I wouldn't round it to 3 places, but round it to 4 significant digits. Okay. Now, any questions about that? You know, you're not going to have, there are whole kinds of physics courses where you learn a whole calculus of significant digits and know exactly what makes sense and what doesn't. We're not going to talk about that because it distracts from the physics. Now, I already mentioned one advantage of scientific notation. Another advantage of scientific notation is that you can see exactly how many significant figures the person is specifying when they give a number. So here is 3.700 times 10 to the 6 meters. That's a big, 3.7 million meters. It's a big number. But when someone writes it this way, I know that they believe the 3 has some important information in it. So does the 7. So does the 0. This is a 0 and not a 1. And same with this 0. It's not just a placeholder because that person didn't have to specify those zeros. They could have left them off if they didn't really know them. But they bothered to put them in there. And so the convention is, in scientific notation, if you specify a 0 at the end, that means you really believe it's a 0 and not a 1 or a 9. It's not one digit different. Okay, so I can see how many significant figures this person has specified. That's pretty good accuracy there. As opposed to the standard way of writing this, 3.7 million or 3,700,000 meters, when someone writes this, it's unclear how many significant digits they believe. In other words, do they really know or believe that this is a 0 and not a 1 meter down at the end? It's unclear because, to write it this way, I need these zeros as placeholders. And I don't know if they're just there as placeholders or if they're actually conveying meaningful information about the measurement beyond just being a placeholder. So that's a second advantage of scientific notation is you can clearly communicate how many significant figures you're trying to convey to someone. Okay, so the answer is it's impossible to tell there. That's it. Again, I'm not going to say too much about significant figures. Just be reasonable. Generally, when I give an answer, I'll round to 3 sig figs. If you're doing an exam, you should round to 3 significant figures. I will put that in the exam. Now, let me switch my, I am on the Logitech webcam, so the problem with this whole thing is that it's hard to tell what we're seeing. So let's go back to Zoom here. And I want to display my board here. You guys can't see my board, or can you? Give me a thumbs up if you can see the board. You can see the board. Okay, great. So I'm just going to give one more example, but in writing, because it wasn't in the slides, to make sure we're counting significant digits. Suppose I give the number 0.0037 seconds. And the question is, how many significant figures am I giving? Somebody in the class shout out their opinion of it. 4. It seems like 4, but the answer is 2 in this case. And that is because when we're counting significant digits and we're doing standard things, we always take the first non-zero position, which is the 3 there. I know that, the only reason for putting in these zeros right here, these leading zeros, is as placeholders. They don't hold any information about what the measurement was. In other words, if I change this a little bit to a 1, it would really change the measurement a lot. So there's no question that this 0 here and this 0 here are only placeholders. So that's a number where I'm specifying 3 significant digits. And if I wanted to write this in scientific notation, always in scientific notation, by convention, we put one number before the decimal. So I would write this as 3.7 as the first part of the scientific notation, because we've got 3 significant digits, times 10 to what power? -3, right? So you probably have done something like this before. You say, oh, I've got to go in the negative power direction by 1, 2, 3. I was putting the decimal place there, here. So I need a -3. Okay. Let me see if I can go back to my slides again. I better put it in slideshow mode first. Okay. Then I go here and share screen. Huh. Thought I had it. Got my slideshow mode. Clearly, I need to play around with this on this system. I'm not seeing, well, let's try sharing this. Well, the class is seeing my slideshow mode. The Zoom folks, give me a thumbs up if you're seeing the chapter 1 outline. Okay, so let me take this out of slideshow mode. I've got to figure out how to do this, but let's take this out of slideshow mode and we'll just limp along in here. I'm not sure what exactly I did before, but end show. Let's share. All right, so here we are back here. Let me try to move this over a little bit. Trying to make it so everybody can see it big enough. Okay. I'm hoping now those of you in your rooms and everyone here can see the outline. Last topic in chapter 1. Then we're going to go into the real physics. So dimensionally balanced equations is a guarantee about the kinds of equations you're going to see everywhere in our physics course. In other words, it's more about what kinds of equations we're not going to use in here. Dimensionally balanced means whenever we write down an equation, we know that both sides of the equation are going to have the same dimensions. So if the right-hand side or the left-hand side has dimensions of meters, you know if you see it in Gene Colley's textbook or if I'm writing it on an exam or on the board, the right-hand side has dimensions of distance too, right? So that if I put in all the units so it comes out as meters on one side, the other side I know it's going to be meters. So what's an example of a not dimensionally balanced equation? Well, here's a situation that I might imagine making some measurements. Let's suppose there's a little car that starts accelerating on the x-axis. And I'm going to, at each time t, I'm going to make a table of what its position x was. And I'm going to go by seconds. So when t was 0 seconds on my stopwatch, it was at x equals 0. It was at the origin. When t was 1, it was at x equals 1. When t was 2, it was at x equals 4. So it's going faster now. When t was 3, it was at x equals 9. I said, look, to get the number always at every point, to get the number on the right-hand side, what I do is just square the number on the left-hand side. So I might be tempted to write down an equation that looks like this. X equals t squared is what I found out. This is called a not dimensionally balanced equation. And the reason that it's dangerous is that if you write it down, you knew how to use it, but somebody else might not know what you meant to do when you did that. Someone might think, well, maybe what I do is measure t in seconds, and then I should interpret x in kilometers. Right? How do they know when they just see that equation? It doesn't tell you what units you use. So this may make sense to you, but it's not going to make sense to everyone else. So in order to be unambiguous, the problem with this equation is it's got dimensions of length on the left-hand side, and it's got dimensions of time squared on the right-hand side. They don't balance out, so it's not a dimensionally balanced equation. You'll never see anything like this in Gene Colley or in the work that we write down. Instead, you'll see things that look like this. X equals a constant that has the numerical value 1, but it's got some units with it, right? So this is telling me look, if I put in t in seconds, right, I'm going to get seconds squared coming out of this part. That will cancel the seconds squared in the denominator, and I'll be left with meters on the right-hand side, and I know exactly what units goes with the numbers that I compute on the left-hand side. It's going to be meters, right? If I put in t in days, well, I'm going to have to do some unit conversion to get things to cancel out before I do that. So that's one interpretation that sort of matches up with the equation on the left. But someone else might say, oops, that they interpreted it to be x equals 1 kilometer per second squared. Now, if I put t in seconds, x would be interpreted in kilometers, and that would be an object that's moving much faster, right? In the same amount of time, it's going much faster. So by putting in those units, and you'll see lots of this in Giancoli, he's making it dimensionally balanced, and that means we always know what, if we plug in certain units, what the units of the thing that we're calculating out are. Here's an equation. If you've ever taken physics before, you probably remember something like this equation. We'll be talking about it pretty shortly. It looks sort of somewhat complicated, but the idea is it's in Giancoli. It's a dimensionally balanced equation, and that means if I plug in all the correct SI units for all the symbols on this right-hand side over here, I know it's equal to an x value, and x in here means a distance, right? It's a distance on the x-axis, really an x coordinate. And so I know the dimensions of the left-hand side are distance, therefore the dimensions of the right-hand side are distance, and if I plug all SI units into the right-hand side, meters, meters per second, seconds, and so on, I know I have to get the SI unit for distance. And so even though I'm not going to work out all the horrendous details of making sure all the units cancel, I know if I just plug in the SI units, just the numbers over here, at the end, without thinking about it, I can just slap on a meters at the end of it. I don't have to keep track of all those units and cancel them out, unless I need to do some unit changing. But we're often going to do problems where we plug in all SI units and we feel comfortable. Oh, I know the answer is a distance. It's got to be meters. I threw in all SI units in. I'm going to get SI units out. The same thing is true if I solve for something. So for example, if I solve for this symbol Vx0 there, the formula looks like this. And I know the interpretation of Vx0 is a, what we'll call a velocity, but like a speed, it has SI units of meters per second, right? In terms of the fundamental units. So if I unthinkingly put all the numbers in SI units on this side, I don't have to worry about the units. I just slap meters per second on the answer at the end, and it saves me a lot of thinking. So you'll see me being lazy about things like that, and sometimes I'll even not write the units in, and I will say verbally to you. Now, normally you do need to put the units in if they're not all SI units, but if they're all SI units, I'll leave the units out and I'll say, I know the answer is going to be a time. So it's going to be in seconds because I put all SI units in. I get the SI unit for time out. That saves us a lot of work as we go on. Okay, so that's the end of chapter 1. And, you know, for today, I think this is just a good, clean stopping point. We could go on into chapter 2, but I think rather than do that, I'd rather have you look at the chapter 2 stuff before we start it tomorrow, and that's where we'll pick up there. Any questions, either from the Zoom folks or those here? I guess I should mention, tomorrow, if you can come, we're going to be meeting in Young 110, and the start time will be 12:55, not 12:50. Okay, we're going by what I said earlier on. And I haven't been in Young 110, but I'm told that there should be enough seating, and more than enough seating for our class in there. And we'll begin into chapter 2. So I believe what I have on the stuff that you're supposed to do today is the videos on chapter 1 and the first sections of chapter 2. And I know it's a little bit heavy at the beginning because we're sort of that startup cost of the first day. We need to be prepared for the second day. But hopefully it's one group of sections roughly per day. Still a lot, but we need to keep up with it. So tell me if you're drowning in stuff. And also make sure that you can see the website and that you can see the Quest site and see our class on there so that you can start being aware of the homework. Any questions? All right. Thank you for your patience. If anybody wants to stay afterward now, you're welcome to ask me individual things. I'll leave Zoom on for a bit if the Zoom people want to hang out, and I'll try to pay attention to the chat as well, because for some reason we're having trouble hearing each other. I'm hoping that by next week, almost all of us are here in the class and everything becomes, as normal as it can be, given that we're all spaced far apart and we all have to wear masks. I avoided doing a thing where people go around and say their name and a little bit about themselves because I thought it would be too awkward with the Zoom folks, and it appears that would be right.